See if this is working. Okay. All right, let's see if everything's working. So my goal is to sort of stream a dynamics class to help you if you're struggling in dynamics. I'm going to follow the schedule that I've used in the past and that the university I'm affiliated with has been using. And I'm getting used to Twitch. So I'm sure there'll be some shaky parts, but if you see anything that is obviously wrong or I miss a sign, please point it out, and we'll work from there. So we're going to be working with dynamics, and with dynamics, what we have with dynamics is bodies in motion. So we're going to be looking at examples where the problem isn't static. So the first class you would have taken is engineering statics. And statics means that our bodies are going to be at rest. And the main difference between dynamics and statics is with statics, we're going to have the sum of our forces. It comes from Newton's law. So the sum of our forces is equal to mass times acceleration. And in statics, this is always going to go to 0. But in dynamics, we're going to have the sum of our forces is going to be equal to the actual mass times some acceleration, and it's not going to be 0. And then when we're working with rigid bodies, we'll have the sum of our moments is equal to 0 in statics. And here we'll have in dynamics, the sum of our moments is equal to a moment of inertia times our angular acceleration. So that's the main difference between statics and dynamics. When we're working with statics, there's two main types of problems we'll be working with. We'll be working with kinematics problems. And what kinematics problems are there the geometry of motion. So what this means is if we have time, position, velocity, position, velocity, and acceleration. If we don't know some of them, we're able to find the relationships between them. So the other type of work we'll be doing with dynamics is we'll be looking at kinetics problems. And what kinetics problems do, it's the study of the relationship between the forces. So what causes the motion? And we're going to start out with these kinematics. And what we really want to do is start out with something called rectilinear motion. And what rectilinear motion is, it's motion in one dimension. And the book that I'm going to be following is Baron Johnston, and they're up to the 12th edition now. But this, if you follow it, is going to be chapter 11.1. And what I want to do right now is define a few things. So if we have a position, what we have is a position in space. So if I have a position and at time 0, I'm in this point right here. So this is some position x at some time t. Now, some time is going to pass, and I'm going to move to this new position. And this new position is going to be this, whatever this is right here. So this is going to be some delta x. So my new position is going to be x plus delta x. And my time this is going to be some change in time. And so this is going to be some t plus delta t. Now, because I have a change in position over some time, I'm going to call that a velocity. So my average velocity is going to be whatever this change in distance is over whatever my change in time is. So it's going to be change in x over change in time. Now, while this is useful, what we want to do is we want to keep making this change in time and this change in x get smaller and smaller. So as we make this smaller and smaller, what we're going to do is we're going to say that my instantaneous velocity is going to be the limit as delta t approaches 0. So I get smaller and smaller and smaller here. So at some point, I have a limit where my delta t is so small it's approaching 0. And it's going to be whatever this change in x over change in t is. Now, we know that we can't have a 0 in the denominator. So this really just becomes the change in x dx over the change in t dt. And this is the derivative of x with respect to time. And this is a very important equation that we have and that we'll be using today. Now, so that's our velocity. And if we do acceleration, what we'll have is with the acceleration, if I have some velocity, again, at time t, and then at some time t and delta t, my acceleration is going to change, or my velocity is going to change. So this is where it was at time t. At time delta t, it's bigger or smaller. So here's some v, here's some delta v. My average acceleration is going to be the same idea. My average acceleration is I'm going to make these time steps smaller and smaller. So my acceleration is going to be equal to the limit as delta t approaches 0 of my change in velocity over my change in time. And again, that's my average acceleration. My instantaneous acceleration, my average acceleration will be just the delta v over delta t. My instantaneous acceleration is when I make that limit approach 0. And as I do that, I get that this is equal to dv dt. So that's another equation that we'll have. And so if I write down the equations that we're working with, I'll have that v, my velocity, is dx dt, and my acceleration is equal to dv dt. Now there's three different equations that we can get for acceleration. If we look at acceleration and we look at our velocity, we'll have that our acceleration is equal to d dt, and we can plug in what our velocity is. So that's going to be dx dt. And what we'll get is we'll get that this is equal to the second derivative of the change in our position. So d squared x over dt squared. And that's another equation that we'll have for acceleration. We don't normally use it that often, but it is an equation that's valid. And the other equation that we will use more often is if we solve both these equations for dt. So if we solve both of these equations for dt, we'll have v dt. We'll have that dt is equal to dx over v, and we'll have that dt is equal to dv over a. And if we equate these two equations, so we say that dx over v is equal to dv over a, and we solve for a, we get that acceleration is going to be equal to v dv over dx. And this is actually an equation that we will use often, and it depends on whatever the initial conditions that are given in the problem are. So these are the four main equations that we will be working with. So 1, 2, 3, and 4. So what I want to do now is I want to go over a couple of different examples that are part that use the position and use the velocity, and these are problems from the back of the book. Now, the problems that we're going to be working with never really get harder. The only thing that really is going to get harder is the functions that we're using, but the steps that we take are always going to be the same, and they're always going to follow the equations that we're working with right here. So let's look at this problem right here. And in this problem, we have that the motion of a particle is given by the equation of x is equal to t cubed minus 9t squared plus 24t minus 8. And we're told that this is in inches. And what we want to do is we want to determine the time when velocity is 0. And we want to determine the position and the total distance traveled when our acceleration is equal to 0. Now, what we have to remember is that if we have a position, if we take the first derivative, we get the velocity. If we take the second derivative, we get acceleration. And this is always the relationship that we're going to use. So if we want to go down, we're always going to differentiate. And if we want to go up, what we're going to have to do is we're going to have to integrate. In this case, we're given a position. So we want to figure out the velocity and the acceleration. So we're going to differentiate our function. And then we have some conditions for part A and part B. So first, let's figure out what our velocity is. So our velocity is going to be the derivative of our position with respect to time. If we write this out, we're going to have that this is equal to the derivative of t cubed minus 9t squared plus 24t minus 8. And we differentiate with respect to time. So our velocity here is going to be 3t squared minus 18t. I forgot a t here, but plus 24. And there is no, when we differentiate the 8, it goes away. And what we want to do is we want to determine the time when our velocity is 0. So what we'll do is we'll say, okay, we're going to plug in a 0 for velocity, and we're just going to solve this equation, 3t squared minus 18t plus 24. What we can do is we can take a 3 right out. So we'll have 0 is equal to t squared minus 6t plus 8. And now we just have to solve this quadratic. So we'll have, what will we have? T minus 4 and t minus 2. So we know that the times that we have are going to be t is equal to 4 seconds and t is equal to 2 seconds. And these are the times that our velocity is going to be equal to 0. Now, velocity is a vector, so that means once our velocity goes to 0, it's going to be switching back from going, say, to the left and to the right. So we're changing our direction whenever our velocity hits 0 and changes its sign. Okay, so we've determined the time when the velocity is 0, and now we want to determine the position and the total distance traveled when our acceleration is equal to 0. So for part B, let's look at that. How do we get acceleration? Well, acceleration is going to be the change in velocity over the change in time. We have an expression for velocity. We found that in part A. We have an expression that our velocity is 3t squared minus 18t plus 24. So we'll just differentiate that. So acceleration is d of 3t squared minus 18t plus 24. And by doing that derivative, we'll get that my acceleration is equal to 6t minus 18. And we're asked to figure out the position and total distance traveled when my acceleration is equal to 0. Okay, so to figure out the position and total distance traveled when acceleration is equal to 0, we need to solve whatever this time is. Once we figure out what this time is, we can plug it back into our equation for distance up here. So if we have my acceleration is equal to 0, we'll get that 18 is equal to 6t, and we'll have t is equal to 3 seconds. Okay, so we know that at t is equal to 3 seconds, t is equal to 3 seconds, we need to figure out what my position is. So my position, x, of 3 seconds is going to be 3 cubed minus 9 3 squared plus 24 times 3 minus 8. So let's do that. 3 cubed minus 9 times 3 squared plus 24 times 3 minus 8. And we get a position of 10 inches. So we need to keep track of this 10 inches. But that is the position at when a is equal to 0. Now we need to figure out the total distance traveled. The total distance traveled is a little bit trickier because we just have to keep adding up the entire distance from when time is equal to 0 to time is equal to 3 seconds. So we also need to figure out our particle's position at each of the times that are important, which is going to be 3 seconds, which we just did. We'll have to look at whatever is happening at 2 seconds because our velocity is changing. But we don't care right now about 4 seconds because that's outside of the scope of when our acceleration is equal to 0. So let's start right here. At x is equal to 0, what will at x is equal to time 0, where are we? We know that we're going to be at minus 8 inches. So x of 0 is minus 8 inches. So let's draw a number line. Let's do this a little visually. And this will be 0. Over here, we'll just call it minus 8. So we need to figure out, this is x at 0. We need to figure out what x at 2 is. So x at time is equal to 2. We put time is equal to 2 into this equation. So 2 cubed minus 9 times 2 squared plus 24 times 2 minus 8. So 2 cubed minus 9 times 2 squared plus 24 times 2 minus 8. We get that this is equal to 12 inches. So we're going to be over here. And then so let's just also say this is time is equal to 0, time is equal to 2, and then at time is equal to 3, we're going to be at 10 inches. Time is equal to 3. We're at 10 inches. So what we're doing is we're going like this. We're going all the way over here. And then we're adding this. So we know that this is a distance of 2. And we know that from minus 8 to 12 is going to be 20. So my total distance is going to be equal to the 20 plus 2, or this is 22 inches. So that's the total distance that I've traveled. So this is probably the simplest type of problem that you can have when you're given the motion of a particle and you're asked to figure out the velocity and the accelerations. And this is the steps that you'll take. Again, it's not that the problem gets harder, it's that the function that you're given up here can get harder. You could have a sine and a cosine in it, you could have an exponential in it, and then the derivatives get slightly more difficult, but the process always stays the same. So now I want to look at a different problem. And in this problem, we're given the acceleration of a particle, and we're told that it's given by the equation a is equal to 9 minus 3t squared in feet per second squared. And we're also given some initial conditions, that the particle starts at t is equal to 0, v is equal to 0, and x is equal to 5 feet. And what we want to do is sort of the same thing we did in the last problem. We want to determine the time when the velocity is 0, the position in 0 again, the position and velocity when our time is equal to 4 seconds, and the total distance traveled by the particle from t is equal to 0 to t is equal to 4 seconds. So it's very similar to the problem we just did, except instead of taking derivatives, we're going to have to take integrals. So let's start by figuring the other thing that's difficult about these problems is sometimes always knowing what equation for the acceleration to use. So we have those really two equations that we can use where our acceleration is equal to dv dt and our acceleration is equal to v dv dx. And how we choose the acceleration equation that we're going to use is going to be whatever the problem's giving us for initial conditions. So in this case, we're given that t is equal to 0, v is equal to 0, then x is equal to 5 feet. So really, it stands out that I should probably use this equation right here because we're going to be looking for a time. If we try to use this equation, we're not going to be able to figure out anything that's happening with time. So let's start this. We want to figure out when the time when our velocity is 0. We know that our velocity is 0 at 0 seconds, but there's going to be other times where we are given a velocity of 0. So let's start by saying that our acceleration is equal to dv dt, And now we're going to plug in our acceleration, the equation we have for acceleration. So this is going to be 9 minus 3t squared is equal to dv dt. What we want to do here is we want to separate and we want to integrate. So now I can bring the dt to my function, and I can get 9 minus 3t squared dt is equal to dv. Now when I integrate, the tricky thing I need to do now is figure out what my bounds of integration are. So when I'm looking at this, well, I'm trying to figure out a time when my velocity is 0. So for my time, I'm just going to go to some time that I'm going to be solving for. And I'm going to have a velocity which is equal to 0. And then at my lower bound, it's sort of what's given here. That I know at time is equal to 0, my velocity is equal to 0. So at time is equal to 0, my velocity is also equal to 0. Now when I'm doing this right now, I'm not going to plug in that 0 just yet. I'm going to keep that as a v, just so it's a little, we can work through a few more of the steps. But do know that I am saying that this velocity needs to be 0. So what do we do? Well, we integrate this equation. Well, this side of the equation becomes 9t, and then this is going to be minus, what is this, t cubed. And this is going to be evaluated from t to 0. And this side is going to be just v. And this is why I kept the variable v. So we're going to evaluate this from v to 0. Okay, so now this is going to be, what, 9t minus t cubed. When we evaluate at 0, both these terms go away. And this is going to be equal to my velocity. And when I put the 0 in, the second term goes away. And I want to figure out what this is. So when v is equal to 0. So when v is equal to 0, what I can do is I can take a t out of this equation. I can say t times 9 minus t squared is equal to 0. Well, we know that first t is equal to 0. We were given that right in the problem. So what we're doing is we're looking for 9 minus t squared is equal to 0. And when we solve that, we get that t is going to be equal to minus 3, and t is going to be equal to plus 3 seconds. Again, in dynamics, most of the time when we get a negative value for a time, we don't really care about it. We're going to discard it because it happens before the problem of interest is going on. So in this case, we only care about our positive 3 seconds. So we have that the time where velocity is 0 again is going to be 3 seconds. So now we want to figure out the position and the velocity when t is equal to 4 seconds. Well, the velocity becomes very easy. We have that already. So we have the equation for velocity. All we need to do is plug in a 4 for t. So we have our velocity is equal to 9t minus t cubed. All we have to do is put in a 4 for our time. And this is going to be equal to 9 times 4 minus 4 cubed. And we get that our velocity is going to be equal to minus 28 feet per second. So that part was easy. Now, how do we get the position? Okay, well, we know that if, right, we had position, we have velocity, and we have acceleration. We said that when we're going down, we're differentiating, and when we're going up, we're integrating. So what we need to do is we need to take our velocity function, we need to integrate it again, and we'll have an expression for our position. Okay, so we know that our velocity is dx dt, and we can just put in now our velocity on, we can substitute our expression for velocity. So we'll have 9t minus t cubed dt, separate and integrate, is equal to dx. Now we need to figure out our bounds of integration again. Okay, so at time 0, we know that at time 0, our position is 5. We don't know what our time x is when t is equal to 4. And I'm going to start just by using t, then I'll put in the 4, just like I did with the velocity. And what do we get here? So this is going to be 9t squared over 2 minus 1/4 t to the 4th. And this is going to be evaluated from t is equal to 4 to 0. And this is going to be equal to x evaluated from x to 5. Okay? I just like to get the expression for whatever x is. So in this case, I'll have x minus 5 when I evaluate this side is equal to 4.5 t squared minus 0.25 t to the 4th. And I can say x, or x of t if I want to, is equal to 4.5 t squared minus 0.25 t to the 4th plus 5. And at t is equal to 4, I just need to plug in whatever 4 is. So x of 4 is 4.5 times 4 squared minus 0.25 times 4 to the 4th plus 5. And I get that this is equal to 13 feet. So that is my position after 4 seconds. Okay, and then finally, we just need to figure out the total distance traveled by the particle from t is equal to 0 to t is equal to 4. And again, we pay attention to, we need to figure out our position every time our velocity is equal to 0. So we have a starting position. We don't care that our velocity is starting at 0, but we just need to know what our starting position is. So our starting position is at 5 feet. Now, when we're looking at this, we don't say we've already moved 5 feet. This is our 0 position. So we're starting at a position of 5 feet. And then where do we need to go? We need to go to 4 seconds. And we need to keep in mind that we have to figure out our velocity at 3 seconds. So let's do that. So my velocity, my position at 3 seconds. So x of 3 is 4.5 times 3 squared minus 0.25 times 3 to the 4th plus 5. And we get that this is equal to 25.25 feet. Okay, so at t is equal to 3 seconds, we go here, and we'll say this is 25.25. And at t is equal to 4 seconds, we'll have 13. So again, it's whatever this distance is plus whatever this distance is. So my total distance is going to be, well, this is going to be 20.25. And this is going to be 12.25. So this total distance traveled is going to be 32.25 feet. So this is just the example of how now, if we were given an acceleration, we can do the same thing we did in the last problem, except we had to integrate instead of differentiate. The next problem I want to go over, all we're going to do, we're going to work the same type of problem with acceleration, except the function is going to get a little more difficult. So the idea doesn't change, just the function makes it more difficult. So we're told that a ball is dropped from a boat so that it strikes the surface of a lake with a speed of 16.5 feet per second. While in the water, the ball experiences an acceleration of 10 minus 0.8 velocity in feet per second squared. If the ball takes 3 seconds to reach the bottom of the lake, determine A, what the depth of the lake is, and B, what the speed of the ball when it hits the bottom of the lake will be. So, in this case, our acceleration is a function of velocity. However, we still need to figure out which function to use. Is acceleration dv dt, or should I use acceleration is v dv dx? So initially you might think I should use v dv dx, but we're given information about how long the ball takes in seconds, and that's our initial conditions with speed. So really, again, we want to use this equation. And we chose that because we're told from our initial conditions it takes 3 seconds to reach the bottom of the lake. And we have an initial speed of 16.5 feet per second. So let's do this. My acceleration is equal to dv dt. And my acceleration is now 10 minus 0.8 v is equal to dv dt. So what I want to do now is I want to separate and integrate just like I did in the last problem. So when I separate and integrate, I'll have, well, right, this is an expression with velocity, so that needs to come to the right side. dt needs to go to the left side. So I'll have dt is equal to 1 over 10 minus 0.8v dv. Now, this is what I was saying. The function makes it harder, but the idea stays the same. So let's figure out our bounds of integration. So our bounds of integration are going to be from, well, at 0 seconds, we start with 16.5 feet per second. And at some, well, we're really doing part B first. But at some velocity, which we're going to find when t is equal to 3 seconds, right? So at time 0, we're moving at 16.5 feet per second. At 3 seconds, when we reach the bottom of the lake, we're moving at some velocity, which we need to solve for. And then this is where it gets a little trickier. You have to remember some stuff from calc if you're not using, if your calculator doesn't do this. But what we'll do is we'll use u substitution. So I'll say that u is going to be equal to 1 over 10 minus 0.8v. So this right, no, I'm going to say u is going to be equal to, 10 minus 0.8v. So when I substitute this right here is going to be 1 over u, which is an integral we know. And then this is dv. Now, we need to relate this dv to du. So with u substitution, we're going to have to do du with respect to v is going to be, well, this just becomes minus 0.8. Now, we need to substitute in this dv right here. So if we solve for dv, we're going to get that dv is 1 minus 1 over 0.8 times du. So now we put that into this equation, and we get that this is equal to, and we still have our bounds of integration. So from v to 16.5. So this is from v to 16.5. We're going to have 1 over u. And we need to put in this minus 1 over 0.8. And this becomes du. So this is, right, just u substitution from calc 2. This side stays the same, so this is still dt from t is equal to 3 to 0. And now this is a integral we know. So this is going to be t evaluated from 3 to 0 is equal to minus 1 over 0.8 times the natural log of u, which is going to be evaluated from v to 16.5. And now what I'm going to do is just substitute back in what I know for u. So u is equal to this 10 minus 0.8v. And this will be evaluated from v to 16.5. All right, so here, now let's just keep this in terms of t like I've done before, just so we can get an expression. So t is going to be, we'll multiply this by minus 0.8 times t is going to be equal to the natural log of 10 minus 0.8v minus the natural log of, well, this becomes a number, 10 minus 0.8 times 16.5. So that's minus 3.2. Okay, so if we use the property of logs, we can get that this is equal to minus 0.8 times t, and this is equal to the natural log of 10 minus 0.8v divided by minus 3.2. This is properties of logs. And then we want to exponentiate both sides to get rid of the natural log. So I'll have e to the minus 0.8t is equal to 10 minus 0.8v over minus 3.2. Let's multiply that and bring it to the other side. So we'll have minus 3.2 e to the minus 0.8t is equal to 10 minus 0.8v. And right, we're trying to figure out what our velocity is. So we just need to solve this for v. And to solve this for v, we're going to have to subtract over the 10. So v is going to be minus 3.2 e to the minus 0.8t minus 10. And then v is, let's divide 3.2 by 0.8. So 4 e to the minus 0.8t, and then 10 divided by 0.8 is 12.5. And so now, right, we're figuring out what my velocity is at 3 seconds. So that's really when I was taking my bounds at 3 seconds. So I just need to put 3 in for this t right here. So my velocity is going to be equal to 4 e to the minus 0.8 times 3 plus 12.5. 4, where's e? E to the minus 0.8 times 3 plus 12.5. I get 12.86. So 12.86 feet per second. This right here is actually part B. But now we want to figure out the depth of the lake. So to figure out the depth of the lake, we need to integrate again. So now when we integrate again, we need to take this expression, integrate it, and that will become our depth. So if we say velocity is dx dt, right? We now say dx is equal to v dt. I have an expression for v. My expression for v is right here. So dx is equal to 4e to the minus 0.8t plus 12.5. I need to integrate. I need to figure out my bounds. Well, we are going from 0 to t, which is equal to 3. And x, well, we don't know our depth. And we're going to start at 0, right? sort of, if we start at the surface, we're trying to figure out how far down we have to go. So this will be 0. This will be whatever our depth is. Okay, so, right, this one becomes easy. This is just x is equal to, well, what do we have here? We have an exponential. So when we take the integral of an exponential, we're going to have 4 divided by minus 0.8 e to the minus 0.8 t plus 12.5 t evaluated from 3 to 0. Need a little, get a little more space. Okay. So now, what's 4 divided by minus 0.8? Minus 5. So x is equal to minus 5 e to the minus 0.8 times t plus 12.5 times t. And you just got to be a little careful. When you're dealing with exponentials, this 0 doesn't always mean that this exponential term is going to go away. So we can't just say it's equal to 0. We have to say, okay, we need to set this to 0. So this is equal to minus 5 e to the minus 0.8 times 3 plus 12.5 times 3. And then we have to, well, this term is going to go away when we have a 0, but this term is not. It's just going to be minus a minus 5, right? E to the minus 0.8 times 0 is e to the 0, which is 1. So e to the 0 is 1. So we just have this 5 that's hanging out. Okay, so we can just put that in our calculator. 5 times minus 0.8 times 3 plus 12.5 times 3 plus 5. And we get plus, doesn't seem right. Where did I mess up? There we go. Forgot the minus. So this is equal to 42.05 feet. So again, it's not harder, or the steps are the same. The function makes it harder. Okay. So I have one more example I want to go over. And this last example, we're going to try to do another acceleration example. And in this problem, we're told that the acceleration of a particle is defined by the relationship a is equal to minus k times the square root of v, where k is a constant. And we know that x is equal to 0, and our velocity is 81 meters per second at time 0, and our velocity is 36 meters per second when x is equal to 18 meters. We want to determine the velocity of the particle when x is equal to 20 meters, and the time required for the particle to come to rest. Okay, so finally, need to reset my pen. So finally, we have a case where we need to use A is equal to V dV dx. Why is this the case? Well, we're looking for the velocity of a particle when we're given x right here. So we know A is equal to minus k times the square root of velocity. So let's use the equation we have. We're not asked anything about time, which is why we can't right now, for part A, use A is equal to dv dt. This second piece of information, x is equal to 20 meters, like we wouldn't be able to put it in that equation. Okay, so A is equal to v dv dx. My acceleration minus k times the square root of v is equal to v dv dx. So now we have to get our variables together. Minus k dx is equal to v over the square root of v dv. Well, this will simplify to the square root of v. So I'll have minus k dx is equal to the square root of v dv. All right, so now let's figure out our bounds of integration. When we're doing and looking at this k, k is a constant, so it can come outside of the bounds of integration. And we want to integrate the velocity of the particle when x is equal to 20 meters. So here we'll have x is equal to 20, but again, I'll keep it as x while I'm performing the integration. And x is equal to 0, v is equal to 81 meters per second. So here we'll have x is equal to 0. Here we'll go from 81 to some velocity v, which is what we're looking for. Okay. Again, what is this integral? V is really v to the 1/2. If I take the integral of v to the 1/2, this becomes, I have to, divide by 3/2 and add 1. So this becomes v to the 3/2, 2/3 v to the 3/2. Again, it's fun with Calc 2. So here we'll have minus k x, which is evaluated from x to 0. And this is equal to 2/3 v to the 3/2, which is evaluated from v to 81. All right, so this is minus k x, and this is equal to 2/3 v to the 3/2, and minus, what is that? 2/3 times 81 to the 3/2, 486. So minus 486. So now we just have a little problem. We know that x is going to become 20. I think I'm off the screen, but we know that this is going to be set to 20, but we don't know what k is. And we weren't asked to find this as a function of k. But we do know we have these initial conditions right here. So by using those initial conditions, we'll be able to solve for our value of k. So to do that, we'll say that minus k times 81. No, sorry, wrong initial conditions. Our initial conditions are here. So we have minus k times 18 is equal to 2/3 v. So 36, 3/2 minus 486. Now we can just solve for k. Minus 486 divided by 18 times this minus 1. And we get k is equal to 19. So now we can do the same thing we always did. And when we have k is equal to 19, we can just put it into this equation. So we'll have minus 19 times x. And we know that x, we said, is going to be 20, right? We want to figure out the particle when x is equal to 20. So minus 19 times 20 is equal to 2/3 v. We don't know what v is, so we're going to have to solve for that. Times to the 3/2 minus 486. So let's do that. Minus 19 times 20. Now we're going to have to add 46. Now we're going to have to multiply by 3, divide by 2, and raise it to the 2/3. And we get a velocity, v, that's 29.3 meters per second. So that's our velocity. Okay, now we're asked for the time required for the particle to come to rest. Okay, because we're working with time, we want to use this equation we have for acceleration. So let me move all of this just a little closer. And let's do part B. Here, my acceleration is going to be dv dt. All right. So now that I have my acceleration is dv dt, I have an expression for acceleration. Acceleration is minus k times the square root of v is equal to dv dt. But I do know what k is. K is equal to 19. It doesn't change. It's constant. So I have 19 times the square root of v is equal to dv dt. Okay. So now separate and integrate. Minus 19 dt is equal to 1 over the square root of v dv. Again, it's annoying, these integrals that don't always use them all the time. So what are our bounds of integration? Well, we know we're going to go from t is equal to 0 to some time t. That's what we're looking for, right? The time required for the particle to come to rest. Well, at rest, we're going to be 0. At time is equal to 0, we're going to be at 81 meters per second. So now all we have to do is we have to take this integral of 1 over the square root of v. So what is 1 over the square root of v? If we look at that, the way I like to do it is, right, the square root of v is v to the 1/2. So 1 over the square root of v is v to the minus 1/2. Then if I add 1 to it and divide by that number, I'm going to have v to the 1/2 divided by 1/2, or this is equal to 2 times the square root of v. Yeah, it's just a little bit of integrals. So here will be 9 minus 19 t, evaluated from t to 0, is equal to 2 times the square root of v, evaluated from 0 to 81. Okay, so here, well, this is going to be minus 19t is equal to 2. What's the square root of 0? The square root of 0 is 0. So we'll just have 0 minus 2 times the square root of 81. Well, square root of 81 we know is going to be 9. And so minus 19t is equal to minus 18. We'll have t is equal to minus 18 over minus 19. And finally, minus 18 divided by minus 19 is 0.947. So t is equal to 0.947 seconds. So that is how long it takes the particle to come to rest. So just like all the problems we've done, the problem doesn't get harder. It's just the function we're using that makes the problems a bit harder. So hopefully these examples have helped you to understand how we can use the different values for the acceleration. In general, the functions you really want to have a good idea of how to take integrals of are going to be 1 over x, which is your natural log. Anything that's, I consider a standard function, which is like a t or a t squared or t cubed, anything that is just a singular variable like that. You're also going to want to have an idea of the cosines and sines and how they switch to each other. You have to think about, okay, if the derivative is this, then the integral is the other way. And the other one that's really good to have an idea of what's going on is your exponentials. So like exponential of minus 3t or whatever we did. It's just a good integral to know off the top of your head. Some of them, U substitution, sometimes you look at it for a while and it trips you up until you're like, oh, right, that's right, I have to do U substitution. Just practicing, you'll get more used to the type of problems that you're going to be given. If you go through the back of your book and you do if you just start doing problems, you'll see these patterns and you'll just see the patterns over and over again. And, you'll be able to do any of these problems. Maybe you'll get the integral or the derivative wrong, but, it should be enough that you show, at least when I was teaching these classes, you at least show me you know what you're doing. You at least show me that, okay, I know to go from position to acceleration, I need to take derivatives. If I'm going from acceleration to position, I need to integrate. Each professor is different. At least for me, I like, I was always, the final answer means something, but I really care about the process that you take. Uh, anyway, hopefully this was useful. Hopefully you got something out of it. Uh, Plan to come back next week. Next week, focus on kinematic equations. So we'll derive the kinematic equations. We'll work some problems of single particles. Then we'll work multiple particles and how they're uh, combined in some way, and finish up with some pulley problems. So there'll be a few more problems next week to do. Probably they'll take a little bit longer. They won't be pure math based. There'll be some word problems. So have a good week, and I'll be back on next week.